topic is acid-base titration calculations. So what we're going to do is we're going to do an acid-base titration calculation for a strong acid plus strong base. Then we're going to do a weak acid plus a strong base. Now you recall that acid plus base in the Arrhenius or Bronsted-Lowry theories always gives us salt. And your driving force, well, both of the ones that I'm going to use will give you, the driving force will be the weak acid water. And the one I'm going to use first is HCl and NaOH. And the weak acid, of course, is going to be acetic acid, or it could be any weak electrolyte delivering acid, hydrogens, and sodium hydroxide, like that. So we start with the strong acid, strong base. Now in this, what you're going to do is to 25 milliliters 0.10 molar hydrochloric acid is added a 0.10 molar sodium hydroxide solution, aqueous. I should have put aqueous in that one too. Aqueous to generate titration curve. So everybody knows what a titration is now. So fundamentally we're going to have the base titrant, the 0.10 molar sodium hydroxide here, and then we're going to have 25 milliliters of the 0.10 molar hydrochloric acid solution. And the essence of this is to, of course, generate the strong acid, strong base titration curve. Which follows this trend. And the equivalence point for such a strong titration, put that up here, follows at 7. Usually the strong acid will start in the vicinity of 1, pH 1, and then as you add base to it, the pH will shift toward the base range. Okay, so what we're going to do is say for the first calculation here is calculate the pH before we add any base to it. So we're given a 0.10 molar HCl aqueous solution, and of course this is going to give you 0.10 molar in the hydronium ions. So taking the pH equals the minus log of the hydronium ion concentration minus log of 0.10 will give you 1. So that's where we're starting in this titration. Then we'll follow with the addition of, say, 10 milliliters of the base, and then we'll add another 10 milliliters. Of course, we're going to 25, and then I'll do a third calculation which will be 24.999 milliliters. And you'll see we're still in that capacity in the calculation, way short of the pH of 7. So watch for that. Okay, so the second calculation is a limiting reagent type calculation, and that we're going to mix 10 milliliters of 0.10 molar sodium hydroxide with 25 milliliters of 0.10 molar HCl. Now, notice how I've set this up. I've got the base solution, and then over here I've got the acid solution. Now, those are only the reactants. I don't put in the products until I get to where I need to calculate the excess. So, in setting one up like this, if you're reading portions, this is a limiting reagent, set it up like this. So your first setup would be 10 milliliters of 0.10 molar sodium hydroxide plus 25 milliliters of 0.10 molar HCl. Well, the reaction in here, I should have put that up here, would be NaOH plus HCl going to NaCl plus H2O. That is a 1-to-1 reaction ratio. So we in moles, so we need to convert to moles. So when working stoichiometry problems, we want to work them in terms of moles. So moles is molarity times volume. See what I did? Molarity times volume plus 0.025 times 0.10 mole of the HCl. Now you can convert that to a 0.0 I'm going to do 10 milliliters, 0.1, right? I need to. So when you look at this, you have 0.001 mole of sodium hydroxide and 0.0025 mole of HCl. Now, from the reaction up here, this is a 1-to-1 reaction ratio. So if I add 0.001 mole of sodium hydroxide, how much of the HCl am I going to use? Well, I'm only going to use 0.001, and anything over that is excess HCl remaining in solution. That is, the sodium hydroxide is the limiting reagent. And so we subtract this, the 0.0025 mole of HCl and 0.001 mole of sodium hydroxide. And we have the excess mole of HCl in excess. Now, we did generate 0.001 mole of sodium chloride on the product side because we're have to generate the salt. However, you don't have to take into account hydrolysis. Now, when I do the weak acid, strong base, yeah, you're going to have to take into account the hydrolysis. I'll show you how to do that in kind of hopefully an organized format. So, subtracting 0.001 from 0.0025, 0.0015 mole of HCl in excess, along with the salt. this up here now. Now, you can't calculate pH with that, with the moles. You have to calculate it with solution molarity. So what you've done is you've added 10 milliliters and 25 milliliters. You have 35 milliliters now with 0.0015 mole of HCl. So this is 0.0015 mole of HCl in 35 milliliters. And to convert to molarity, you have to divide by the volume in liters. So 25 and 10 is 35. Converted to liters is 0.035 liter of solution. And so dividing that out gives us the concentration of HCl in excess. And so that gives us a 0.0429 molar HCl in excess. Well, this is a strong acid. So while it generates HCl, it also generates 0.0429 molar in hydronium ions because it's 100% ionized. And so from this, we can get the pH for our first addition. We'll call it calculation pH 2. We already got pH 1, which is 1. That gives us 1.4. I'll round it up. Okay, we're adding 10 mils right here. Then this number is 1.4 on the pH scale now. So we're moving up the pH curve, and so we'll go to 20 mils, and you'll see it jumps up a little higher. Now, there we go. The reason I do this and show you all the steps in this calculation is you'll repeat them as many times as you need to until you get to the equivalence point. Now, the equivalence point is a hydrolysis reaction if it's a weak electrolyte. The equivalence point is only a salt left in there, so for a strong, it'll be a 7. So the reason I'm doing this, because number 3 will be an identical copy of this. And will be so converting this data to moles is 0.020 times 0.10, and that's moles. Notice how I tag it with moles. This is solution data, but molarity times volume gives you moles of sodium hydroxide. And you're adding that into 0.025 liters of 0.10 molar, which gives you those 2 times moles of HCl. Yeah, I'm setting this up. I'm just taking the data and then converting to moles in the next step. Okay, then this is just really moving the decimal one place, and that's 0.002 mole sodium hydroxide and 0.0025 mole HCl. And since it's a 1-to-1, all we're going to use is 0.002 mole of the HCl. So that's going to leave a 0.0005 mole in excess. See that? So you just take the difference in those two. That's 0.0025 minus the 0.0020 mole HCl in excess. You're not concerned about the sodium chloride because it doesn't affect the pH. Sodium and chloride do not undergo hydrolysis. So this gives us 0.0005 0.05 mole of HCl excess. And from this, we want to convert it to concentration terms. So we've mixed 20 and 25, so that gives us a total solution now of 45 milliliters. So that is 0.0005 mole of HCl in 0.045 liters of solution. And so the concentration of HCl now in molar terms is 0.01111 molar in HCl, which is of course 0.011 molar in the hydronium ion, because it's 100% ionized. So the point for the third position on the titration curve, pH, at 20 mil addition minus log of the 0.011 would be 1.95. So that brings us, say, at 20 mil addition up to 1.95, just to illustrate what we're trying to accomplish. How this is put together in the repetition of the calculation. Starting with the data, convert to moles, look at the 1-to-1 reaction ratio, and take the difference in the moles, and you find out who's in excess. And then from there, you can calculate your pH. All right? We're going to go 24.999 milliliters of the 0.10 molar sodium hydroxide, and then 25 milliliters of the 0.10 molar HCl solution. So we're pushing right up next to the equivalence point. And how do we start it? Convert to moles and look at the difference. Okay, so this would be in liters, 0.024999 times 0.10 mole sodium hydroxide, and then 0.025 times 0.10 mole HCl. Molarity times volume, of course, in liters. And that gives us 0.0024999 sodium hydroxide. Mole of HCl, like that. Now we take the difference between the HCl and the amount of NaOH that we've added to neutralize that quantity of HCl. See, we're only going to use whatever the amount of moles of sodium hydroxide we used. So that gets you real close. So you will not reach the equivalence point at this amount of sodium hydroxide. So I did a backside calculation to get this number. And of course the pH of that and I get 6.5. So that's the point of all this right here. It has to be equal to this number if you were at 7. Is that true? Yes. So in subtracting these, you shouldn't get 1 times 10 to the minus 7. Well, the calculator mine can't figure to that extreme. So I did another calculation, but you're in this vicinity, say 3.16 times 10 to the minus 7, because you're not quite to that pH of 7. Now, the fifth calculation would be at the equivalence point, and I think you can see it if you do it this way. If you have 25 milliliters of the 0.10 molar sodium hydroxide plus 25 milliliters of 0.10 molar HCl. I didn't mean to confuse you on that one. It's just my calculator wouldn't do a fine analysis. But you have equal moles. HCl. So the only thing remaining in solution at this point is 0.0025 mole of sodium chloride. There is no more sodium hydroxide or HCl because it's all been converted to the sodium chloride plus, put this in there for emphasis, on the product side. But this doesn't enter into our calculation. Now, of course, if you need the concentration of sodium chloride, questions do show up, and you're now 25/25 or 0.050 liter of solution. So that's a 0.05 molar in sodium chloride. Well, as you may recall from our work on hydrolysis, when we look at sodium chloride, it goes to sodium plus chloride, just to review this, and we test the sodium with water. We get sodium hydroxide plus an extra hydronium or chloride plus HOH gives us HCl plus an OH. However, because these are strong electrolytes, no reaction occurs. So that's the reason you're now at pH of 7. So the pH at the equivalence point is dependent only on the autoionization of water. So you wind up with a pH equal to 7 at the equivalence point. Now, beyond that, all you have is excess OHs beyond the equivalence point. And so you're calculating whatever the pH is based on the hydroxide concentration in solution along with some NaCl floating around. And so that's what pushes the titration curve up over the toward 14. Now, of course, we're going to use the HOAC. Well, let me do it with sodium hydroxide first. NaOH plus the acetic acid goes to the sodium acetate, salt, plus the H2O. So we're going to add quantities of sodium hydroxide into say 25 milliliters of 0.1 molar acetic acid, and we're going to go through the same sequences until we get to the common ion effect, and we'll show you how that filters into the issue as we go through this. So here is our basic problem. Add 0.10 molar NaOH into into 25 mils of 0.10 molar HOAC. So we're generating the titration curve, and we're going to do it in, say, 10, 10, and then 25 to get to the equivalence point. Okay, so titration, first calculation is what's the pH of the acetic acid solution before we start our addition of base. So, given 0.10 molar acetic acid with Ka equal to 1.8 times 10 to the minus 5 is a weak electrolyte or weak acid in pure water. So if you have a weak acid in pure water, you can go straight to the square root form. You don't have any common ions here yet. So we have the hydronium ion concentration before addition of base is the square root of Ka times HOAC, which is the square root of 1.8 times 10 to the minus 5 times 0.10 molar and 0.0013 molar in hydronium ions. Even though the acid is 0.1, it can only deliver 0.0013 in molar in hydronium ions. So the pH before addition (2.89). So in our titration curve, it's starting at zero volume at 2.88 or 2.89. And now we're ready to add the first 10 milliliters of sodium hydroxide and repeat the calculation we showed you in the strong titration. Okay. So here is the solution in the burette, just like I'm showing you over on the demo table. So visualize the blue stuff in the burette as a sodium hydroxide, and if we had a beaker under there, you'd see 25 milliliters of yellow, because we'd put of the indicator in there and give you a yellow color, BTB. So what do? Convert to moles and figure the yield out of it. Now, one thing on this is that you're going to have the equilibrium affected because there's going to be a common ion, the acetate ion, present. So follow that. So first thing we want to do is have the NaOH HOAC reaction, find out how much excess acid we have, and then work from there. Okay, first thing, moles. Okay, so we're looking at 0.0010 mole sodium hydroxide, 0.0025 mole acetic acid. So this is, let me do this, NaOH plus an HOAC goes to NaOAC plus the H2O. So here we have a 0.0010 mole. Let me move that over a little bit. And 0.0025 mole. And so what's this going to give us? Well, you're going to have an X after this is consumed. What's going to happen is you're going to have 0 sodium hydroxide, because it's a limiting reagent, right? When you add in, because you got an excess of HOAC. But this one is 0.0025 minus 0.0010 mole, 0.0015 mole of HOAC. But you're going to have sodium acetate, which is the acetate ion. And so if you use up 0.001 mole, it's a 1-to-1. So this is going to be 0.001 mole of the OAC present. Because it's a 1-to-1 reaction ratio here, so you're going to have this in excess, but you'll also have that acetate ion generated in that reaction. So how do you deal with the pH at this point? Well, you're still working with the HOAC, so you have to take that into an HOAC and set up the ice table with these two. Well, I forgot to configure the concentrations and molar concentrations. So what this gives us, and you don't have to worry about this one, this is 0.0015 mole, and we mixed 10 and 25, that's 0.035 liter of HCl, so whatever that comes out to be. And that is 0.043 molar in HOAC. That's the excess. And this one will be 0.0010 mole of the OAC in 0.035 liter solution. That's 0.029 molar in acetate ions right there. So when you get down to the excess acid here, you also have to take into account this one. Once you get and that's always the salt. Whatever the base added will be the same as the salt. Base and salt are the same. However, you have to take the differential to get the excess acid, like we did in the first calculations up there in strong. And this gives you an excess, and then of course you always have to convert them to the molarities. And so from here, you want to set up the ice table and calculate your pH. So from the first titration, after adding the first 10 mils, this will be a 0.043 molar excess in the presence of a 0.029 molar acetate. So you can see those, how those fit into that calculation. And so this starts at 0, we assume. And so minus X plus X, so we're looking for that X. And so 0.043 minus X, and 0.029 plus X. And so there's your equilibrium row, which you now put into the Ka expression. Right here is 1.8 times 10 to the minus 5, and you're looking for that hydronium ion to calculate your pH. And so the This is 0.025 divided by the 0.043, and so your hydronium ion now is 0.04 times 1.8 times 10 to the minus 5.
Doc.
I'll be right with you. Okay, 0.025. And there it is. Sorry. I got 2.7 times 10 to the minus 5 here, and then calculating. And this is just the change that we've gone through. Okay. So, just like we did when we did the strong, and we'll start over and titrate, say we're titrating 20 mils into the 25 mils. So moles would be 0.020 times 0.10 mole. So you're seeing the repetition now, hopefully. And then that is 0.0020 mole. All right. Now, what did we tell you about defining the salt, the amount of salt? If it's always, before you get to the equivalence point, it's always the amount of base added, because the base is going to be the limiting reagent and it's going to be converted to salt. And if you're not equal to the amount of acid, then you have some acid left over. Can you see through the problem a little better now? See, because as you go to each step of the titration, you have to calculate the excess acid and determine the amount of salt generated. And the salt has, of course, the common ion. Then you set up your ice table and calculate your pH from the ice table and the weak electrolyte ionization. So I'll try to be clear about this. So what's going to happen is we're going to have a 0.0025 mole minus 0.0020 mole of HOAC in excess plus a 0.0020 mole of the OAC common ion after you add those two together. Everybody good with that? See how I took the difference, because you have a 1-to-1 reaction ratio. And so that would give us a 0.0005 mole of the HOAC in excess in with a 0.0020 mole of the common ion. Now you convert it to molarities by dividing each one by the total volume in liters. So that'd be 0.0005 mole HOAC. And 20 and 25 is 45, 0.045 liter solution, plus a 0.0020 mole OAC minus over 0.045 liter. Solution. So now we have that in solution and in terms of molar concentrations. Now, to get from here to the pH, you set up the ice table or always around the weak electrolyte ionization. So this is the one you want to set up the ice table and determine the hydronium ion concentration. So initial, change, and at equilibrium. So get it all on the page for you. And so we have 0.011 molar here, 0 and 0.044 molar there. and minus x, and plus x, which is so is that you need to use to calculate your hydronium ion concentration now. So Ka Okay, I get 4.46 times 10 to the minus 6 molar. Y'all back me up on it.
Yes, sir, that's what I got.
Okay, so pH is minus log of course, hydrogen. 4.46 times 10 to the minus 6. 5.35. So you move up on the pH tracing of the curve, and after 20 mils, you're moved from 2.89 up to 5.35. Here is 25 milliliters of sodium hydroxide, 0.1. Plus 25 milliliters of the 0.10 molar acetic acid. So what are you going to have? You're only going to have salt remaining after you conduct the reaction. You have 0.0025 mole of sodium hydroxide plus 0.0025 mole acetic acid. Well, what's that going to generate? Well, there's complete neutralization, so you don't have any acid or base remaining. So the only thing you have is 0.0025 mole of the sodium acetate, which of course we're not interested in the sodium, we're interested in the effect of the acetate ion. So when we test the acetate ion reaction with water, yeah, we get a weak electrolyte. That is OAC minus plus H2O sets up an equilibrium and generates OAC and excess OH. And this is what's going to define the OH is going to define your pH at the equivalence point of this titration. You recall that when you have a weak acid titrated with a weak base, strong base, your pH is going to be in the base range. And if you have a weak acid titrated with a strong acid, a weak base with a strong acid, you get in the acid range for your equivalence point. But anyway, here we have 0.00525 mole of the acetate and disregard the water. So all you're interested in is the effect of the acetate right here. And so we take the initial row here, and this is 0 and 0. Well, of course, we have to convert that to molar concentration. So we have 50 mils, so it's 0.0025 divided by 0.05, and liters, and that's 0.05 molar in the acetate ion. And you still have 0 and 0. Move this down if you want to. 0, 0. Now your change and then your equilibrium are based on that. You're looking for how much OH is generated. So you're starting, this decreases by X plus X plus X, because these are going to be in equal amounts. Now, don't get confused here. Once you get to the equivalence point and you start looking at the effect of the common ion, or the hydrolysis effect, when it reacts with water, it's going to produce equal amounts of weak electrolyte in base, or weak electrolyte in hydroxides, or hydronium ions, whatever you have over here. These are equal. And so that's 0.05 minus X, and you can drop the X, long story short, and you have X and X. Okay, this is where you have to use the KB prime issue, and you have to have the Ka for the acid right there, and then you apply it to the KB prime for the OAC. So KB prime, Ka times Kb is Kw. So we have Kw over the acid K value, that's here, right here. And that's equal to the products over reactants, disregard water. So that would be the concentration HOAC times OAC over the acetate ion concentration, or the salt that you have remaining. So then this gives us 1 times 10 to the minus 14 over 0.8 10 to the minus 5, and that's equal to X squared over 0.05. So you substitute that row in there along with the Ka value. See what I did? And Kw over Ka, and then we solve for X, which is the hydroxide. So you get a POH and then pH, 14 minus POH, and you get your pH at the equivalence point. So that is, well, let me bring it down here so it'll be so crowded. So X, which is OH, is 0.05 times 10 to the minus 14 over 1.8 times 10 to the minus 5 molar. See what that looks like. So your hydroxide is that value, so we can get the POH, we go minus log of that, 10.56, or am I, ooh, I'm missing something, hang on, there, y'all get that? Anybody that's trying? Okay, so POH now is minus log of that. And so that is 5.28. So the pH at the equivalence point is 14 minus POH, which is 14 minus the 5.28. And that's 8.72. So you're pushing right up next to 9, and that's titration. So you're given a titration of HCl into NH4OH. All right. So what you want to work with is, say, HCl plus NH4OH going to NH4Cl plus H2O. And everything's the same as we did in the previous and the weak acid strong base. But this one is a weak base with a strong acid. So let's say you start with a 0.10 molar HCl plus you're adding this into 25 milliliters of 0.10 molar sodium hydroxide. Okay, and so X mils is what you decide to add. And as you go along. Now, you've got to calculate pH before additions, and you're looking, remember that's a square root formula for hydroxide. Now the Kb is 1.8 times 10 to the minus 5 for ammonium hydroxide. Like that. And so your hydroxide concentration initially before reaction, square root of Kb to NH4OH. And so go from there. Then set up second titration, 10 milliliters of 0.10 molar HCl plus 25 milliliters of 0.10 molar ammonium hydroxide. Just like we did. Convert to moles, find the excess. Now, in this case, you're going to have an excess of ammonium ions, and you have to figure the hydrogen concentration. You won't have to go back, it won't be an OH this time. So, as you go through this is a limiting reagent, and this will be the excess until you reach the equivalence point. And so at equivalence point, what's the pH of whatever the molarity comes out? So you've got a 50-50 mix here of NH4 plus the ammonium effect solution once you reach that equivalence point. So it's a 1-to-1 reaction. So if you took 25 mils of the 0.1 acid, 25 mils of the 0.1 ammonia, you'll have the same concentration over here, but the moles over here. So but you got 50 mils now. So that's 0.0025 over 0.05, and so that would be the concentration of your common ion. And so that's what you would have to work with in the ice table down here. I'm going to leave that with you. And by the time you get through that, if you can get through that, you'll be all right. But hopefully you see that these titration calculations bring together a lot of chemistry under one roof, so to speak.